Hello everyone, my name is Gururaj and here is our COA assignment. I will explain we have four programs that I will explain the first program, factorial of a number. To finding a factorial of a number, here is a code. The program starts at some memory address OOH00H. This is the first address in the program memory. Load the number n, whose the factorial is to be found, from memory 60 Hz into the accumulator. Move it into a register R0 will be act as a counter. Example, if n is equals to 0.5 Hz, then R0 equals to 5 Hz. If a equals to 0, then n equals to 0. Jump to the label fact 0. This handle is used to perform the specific case where 0 factorial equals to 1. Initialize R1 equals to 1, which will hold the running product. The factorial value as it is built up. Move A R1, load current factorial result into a accumulator. Move B R0, load current counter N into a register B. Mul A B multiply A into B. The result is 16 bit, lower a bit in A, higher 8 bit is B. Since we only store in a 1 byte, we know only a low byte. Move R1 A, store the byte of the product back in R1. DJNZ R0 stands for direct jump. Factorial loop decrement R0. If R0 is not equal to 0, repeat the loop. If R0 is equals to 0, exit the loop. This repeats will until R0 equals to 0, meaning all numbers have been multiplied. After the loop ends, R1 contains the factorial in 8-bit form. Move it into a, then the store it memory location 61 Hz. SJMP stands for shortest jump path. Creates an efficient loop to store the execution, like a halt instruction. If n equals to 0, the factorial is 1. So store 0, 1 Hz at a 61 Hz. So here we will run the program. First we have to debug it. Then after the completion of debug, we assign the value. After the assigning, we will run the program. And here is the result. Thank you. We will move on next program. Okay, moving on the second program is finding a GCD of a number. Starting org 0 Hz sets the origin starting address of the programming to the address 0 Hz. L jump start long jump. L stands for long jump to the label start. This keeps any interrupt vectors and the jump directly to the main program. Move 62 Hz and the address value is 30 Hz. Store 48 hexadecimal 30 Hz at a memory address of 62 Hz. Moving 63 Hz value of 16 Hz. Store 18 hexadecimal 12 Hz at a memory address of 63 Hz. Call GCD underline sub. Calls the substitution that computer the GCD. Yes jump start for the shortest jump keeps the jumping to the same address, means current location, so the program starts running. Further acts like a halt. Load the two number from a memory into the registers. R0 62 Hz first number and the R1 63 Hz second number. Now the algorithm will repeatedly subtract the smaller number from the larger one until the both are equal. Move a R0, load R0 into the accumulator. CLRC. CLR stands for clear. C means carry. Clear screen flag the before subtraction. SUBB A. SUBB stand for subtract R1. Subtract R1 from A. A equals to R0 minus R1. JZ G equal. If result is a zero number or equal GCD found. GC R0 less. If carry equals to 1. Give R0 less than R1. Jump to the R0 less. Move R0 A. Otherwise update R0 equals to R0 minus R1. The difference. S jump G loop. Repeat the loop. If R0 is smaller, subtract R0 from the R1. That is R1 equals to R1 minus R0 and go back to the loop. When R0 is equals to R1, the value is the GCD. Store the result into the memory location 64 Hz. RET return to the main program. marks the end of the store file. Next, we moving on the execution of the program. Here, we will first debug the program. After the completion of the debug, we assign the value to the program. After the assigning value, we run the program. And here is a final output. Moving on our third program, which is the finding of square of n natural numbers. So here is a program. The starting org 0 hertz. Place this reset vector at a 0 hertz and jump to start. Org 30 hertz. Place the main code starting at the program address 30 hertz. Optional layout detail. Starting our first line, move A to 67 Hz. Load N from the data memory 67 Hz into accumulator A. Move R5A. Copy N into the RS. R5 will be used to jump into loop counter DJNZ decrements R5. Move R3, value 1 Hz. Set R3 equals to 1 means R3 is the current index I. 1, 2 up to N. Clear 68 Hz or clear 69 Hz. Clear the 16-bit accumulator 69 Hz is to 68 Hz. Sum equals to 0, JZ. Done. If A equals to 0, that means N was 0, jump to done, skip loop. See bug not below. Loop mul AB. Mul stands for multiple. And next line, move A, R3 and move B, R3. Prepare operands. Mul A, B computes R3 into R3. Result low byte given A, high byte is B. Move R4, A. Save the low byte of the square on into R4 temporary. Move A 68 Hz, add A R4 or move 68 Hz A. At the low byte of the square of low sum 68 Hz, no carry is handled here. Add only effects CY if overflow from the low byte occurs. Move A 69 Hz, ADDC A, B. ADD means add, stands for addition. Move 69 Hz A. Add high byte of the square plus the carry from the previous add via add carry to the high sum 69 Hz. INC R3. INC stands for increment index to the next integer. DJZN R5 loop. Decrement R5, count remaining numbers. If not 0, jump to the loop. And final last line, E done. Yes, jump, halt. Infinite loop, not labeled in E done. After the completion of explanation of the program, let's move on the execution part. So here is the execution. We are assigning a value first. After the completion of debug, after the completion of assigning the value, the running of program. Here is the output. Thank you. Next, move on our last program. So finally, moving on our last program, which is of finding the square of a number. The starting a program org 0 Hz L jump start. Let reset a vector and the jump to the main code. Move A 65 Hz. Move R2A. Load N from the data memory 65 Hz into the accumulator A. Then the copy to R2. R2 equals to N. Move R3 value 0 Hz or move R4 value is 0 Hz. Clear R3 is to R4 will be hold the 16-bit running product. Initially 0, move A R2 or move R5 A. Copy R2 into the A, then side into R5. R5 becomes the loop counter, number of addition to perform. JZ store the result. If A is 0, N equals to 0. Jump to restore result 0. JZ test the 0 flag from the last move. Since A contains R2, this correctly checks N equals to 0. Loop add body repeated addition. Move A R3 means load low byte of a accumulator into A. Add A R2. Add N to the low byte. Move R3A stores updated low byte back to R3. Move A R4. Load high byte into A. Add A value 0 Hz. Add carry from the previous add into high byte. Adding 0 just propagates carry. Move R4A. Store updated high byte. DZ NZR5 loop add decrement loop counter if not 0 repeat. Each loop interaction add n to the 16-byte accumulator. R4 is to R3. After the n interaction, the accumulator contains n into n. Stores result. Move 66 Hz R3 low and the move 67 Hz R4 high. Stores the final 16-bit product in a data memory. S jump halts the program with an infinite loop. This is the explanation of our last program, and we are moving to the execution. For execution, we will debug as usual. After the debug, we assign the value and finally we run. After the completion of running the program, we get the output. Here is the output. Thank you so much.